So I would really like to ask all the other speakers from this session to just join us. And while we do, Rob, I was just wondering on your thoughts on soft versus hybrid, soft rigid. I think there's a bit more of a focus on how do we create softness from rigid materials or combine the two. I was wondering on your thoughts of that versus entirely soft robots and the different motivations or requirements for them.
Yeah, it's a really good question. And I think, again, to quote my colleague Oliver Brock, I feel like the field of soft robotics for the first 10 or so years of its existence. By the way, it started in 1980. It didn't start 10 years ago. But for the last, let's say, 10 years, it's been an alchemy phase where it's like, hey, look what we can make using soft materials. And I can make a soft gripper. I can make a soft arm. I can make whatever it is. And now we're at the point where it's like, okay, I think we understand how to develop that. And there's fascinating, as Sepe was describing, fascinating materials questions that still exist and can be brought to bear. Absolutely. But now I think we're starting to get more towards systems. And if we start thinking about systems, then I don't think anyone would claim that if I want to go replace a more traditional robotic manipulator, that entirely soft system is going to be the solution. There's questions about payload, there's questions about robustness, there's questions about precision and control. But I think that, as you're alluding to, there's some happy medium there where something which maybe has some structural rigidity in certain places, maybe it has the ability to change phase, to lock, take bioinspiration from echinoderms and do some sort of effective phase transitions between rigid and compliant modes, etc. I'm rambling, but I think that the solution is somewhere at the intersection.
Thank you very much. So yeah, thank you very much all for your talks, and thank you for joining us again. One question just to start off is about the use of simulation and the reality gap. And I'm just wondering, because we've seen so many different examples, some which are bioinspiration with Rob's work and Thrish, some which are kind of material polymer science, and then Marco doing fantastic things with simulation and Cynthia using computational tools. Where do you see simulation? Do you see it as a tool that is going to change how we design robots? Does it depend on the domain? Does it depend on the scale? And do you think we can successfully, significantly close the reality gap for it to be used across down to Thrish's robots in the esophagus, or for example? What do you see? Do you see sim-to-real and computational design using simulation as the future? Would anybody like to start us off? Marco, I'm sorry to pick on you, but perhaps I should come to you first.
No. So, for short answer, yes, absolutely. I think we have a great potential here, particularly when we're combining now not only the control aspect and the planning aspect as we did until now, but also the design aspect. And I think this massive growth, also the massive parallelization that we're seeing in many of the new simulators that are coming out, really allows us to generate the necessary amount of data to do that, and also to penetrate the design space a lot more.
I'm just wondering, more on the materials level, do you think that can, let's say we're looking at self-healing, or we're looking at really at the materials level, is simulation a tool there that's useful, or at that level and that complexity of interactions? Rob and Sepe, I don't know what you think of that.
I mean, I'll let Sepe comment on the material level. We don't do much in terms of material synthesis. We use I think similar to what Mark is saying, we use simulations. In fact, we've developed our own, so I'll give a shameless plug for something called SOMO, which is a soft motion simulator that's based on Python and PyBullet physics engine. I think it's an invaluable tool, right? Because we spend a lot of our time figuring out how to prototype robots really quickly. But at the end of the day, if we had a simulation tool that could afford us the ability to have reasonable, and I don't think not even good, reasonable fidelity simulations of soft systems interacting with the environment, then that's an invaluable design tool. And then we can iterate then on sort of sparsely with respect to experimentally to validate some of those results. And then we've also been now working on using those kinds of tools once we have a robot, then applying machine learning and simulation to develop control policies that would be otherwise really difficult to do given the sort of high dimensionality of these systems.
Yeah.
Yes, we are also, we're actually also taking that route to all do the simulation onto the material level and even the molecular level. But I think, there's always a big difference between simulation for design and using the simulation for the control itself. I think if you really scale down to simulation on the material level, it's more for application where those scales are really relevant. And then I think to do the control on those scales, usually the applications there, they don't have the computational power to actually use the simulation in the control itself.
Cynthia and Thrish, I wonder, how do you see simulation helping in the work you do?
I mean, simulations are extremely useful. We do simulations like, so for example, in soft tissue modeling, we take CT scans from real patients and then convert them to CAD models and then get it in the cluster computers to do millions of palpations and then build surrogate models of this stuff. That is extremely useful. But when it comes to real contact, like there's something missing in contact dynamics. Like, so we really don't understand the intricate details of friction models. Like, I mean, we can approximate it to Luger model or Coulomb friction or whatever. So, but when it comes to real friction, there are things more than that. And then the vibration propagation across the body and all those interaction, nonlinear interaction dynamics are much richer in real robots. So it may be that it's a compromise, right? So you get as far as you can with the simulations and then do real world experiments and understand what is missing. So the good thing about doing a simulation is like what you put into the simulation, and then the experimental results tell you what is missing, right? And then whatever you are trying to explain what is missing is extra math you are understanding. So that is good.
Yeah, I'm going to agree with what the people here have said, basically that the simulation can be very useful when we're trying to design robots or design controllers. There is still a gap between reality and simulation, but I'm also going to extrapolate from that a little bit and say that maybe our goal isn't to close that gap all the way. Because a lot of times the systems that we're designing, they need to work in a lot of different scenarios, right? And if there is a controller that you design that works or that relies on your simulation being accurate for the specific situation that you simulated it for, that robot isn't necessarily going to work in real life when that situation is not what you modeled, right? So I think there are some benefits to using simulation to help with design, to help with control. And there are definitely really interesting questions in how we can close the sim to real gap. What practically, when it comes to designing these robots, I think there are ways, or the ways that we approach design don't necessarily require that to happen.
Thank you. And following on from this, we saw some lovely examples of different environments that we're trying to get embodied robots to work in, whether it's under the water, in mountains, very complex terrains, inside the body. Where do you see the future of embodiment? Well, where do we see the biggest potential gains for utilizing embodied interactions? Is it in, perhaps with Thrish, between humans and robots, or understanding that? Is it under the sea? Where do you see the biggest impact for exploiting embodiment in the coming years?
I think it has potential in understanding who we are. And then robots is a good vehicle to understand what is happening in our own body, especially aging, for example. After all these robots, like I have this hypothesis that aging is more about losing the physical side of the computing than losing any brain power or anything. So those, for example, if you change a little bit of viscosity in the cochlea of the ear, and then you lose a lot of bandwidth in the spectrum you can hear, right? You cannot replace that. So I mean, then it informs how to design wearable robots, or kind of a cyborg in the future. How to replace or compensate for the computing power we lost. It is not just muscle power or tone we are losing, it is the computing power also we are losing, right? So, I mean, it is not just ear, the knee joint is a computer, ankle joint is a computer. So they are solving computational problems. And then a little bit of friction change or, cam profile change in the knee joint is about losing computing power. And then if we understand it properly, maybe we can have wearable exosuits to compensate for these things and then get people to have better end of life quality. So that's something I'm thinking about heavily. Yeah.
I think that's a very, very nice and needed research area. Any other thoughts from the panel on applications or environments? Marco?
Yeah, I mean, from my side, I think the biggest change is that we're moving away from a perfectly deterministic environment where we're deploying robots to a much more uncertain environment. I think that's where the embodiment is becoming a lot more important, not only on the mechanical side, but in general. I think we have been seeing tremendous progress in robotics when it's in a defined environment where we designed what kind of environment we want to have for the robot. But now things are changing. We have robots in the real world, and I think that's where these concepts are becoming a lot more important. Whether it's like the robot itself that has to interact, but also like human-robot interaction, whatever, you name it.
I think that's very interesting. And I think actually it comes back to also Thrish's robo-patient. That's something that that's an area which is very exciting. How do humans and robots interact? Any other thoughts? Rob, I'm wondering about your undersea. There's such a blossoming area, kind of also driven off what you've already started in the area of underwater soft robots. Do you think it's a very interesting environment to work in with a fluid in the ocean. Do you think that is an area where we can continue to make significant developments and there are still really fundamental questions to address?
I think, yes. I mean, I think maybe not so much fundamental robotics questions. I think more exploiting the capabilities of soft robots for other biological discovery, for example. So, there's all sorts of anecdotes about what percentage of the world species or the oceanic species have been discovered, and it's very small. And there's other sort of anecdotes about how there's some of these sort of coral species, some of the species that we're interacting with in the deep ocean are thousands of years old. And so I think it's important to take all of this in mind and leverage some of the advances of soft robotics to be sort of gentle and thoughtful about how we interact with the ocean environments. I'll give one more instance, which is another plug. We're part of another project now, which is trying to figure out how sperm whales are communicating, what they're saying to each other and talk back. And so for that, we need a whole bunch of audio data and other data. And so we've been developing soft robots that kind of gently ride along sperm whales. So there's there's not necessarily so much innovation there. There's bits and pieces, but there's not like major breakthroughs that really need to happen for that to happen. But we're heavily leveraging what has been done in the field to be really gentle with all of these interactions with ocean life.
Sounds fascinating, understanding animal communication. Seppi, I'm just wondering about self-healing, and I think it was interesting both as the obvious, okay, great, we can make sensors, we can make skins that we can heal, but I think the other interesting thing you talked about was recycling. Can we reuse these robots? Because I think that's becoming a bigger issue that we need to be aware of, and B, also for construction and fabrication. Where do you see the future of self-healing? And I'm also to the rest of the panelists, do you feel self-healing is something that could change how you approach robot design, or indeed, if you integrated it into your robots, do you see it as a game-changing technology?
I think it is a massive thing. So I was fascinated by Seppi's talk. I mean, especially, those space applications, like, so it's very costly to send, repair people to space, right? So you're talking about Mars colonization and all these things, like, so it's super important to have these structures that can self-heal, when the payloads are very expensive.
Yeah, we see a lot of applications inside of robotics, but also outside. A big problem was already raised or challenged by you, Josie, is that we can get the same properties as used in products today. But I think, we can only just see it by making the application and see if we can actually get the requirements which are imposed by this application. So that's what we're doing now. And with the soft robotics, we see that we come very close to the properties which are used. And then what we will do now is on the long term, see how the lifetime is increased, but those measurements are also a bit difficult because we need to do a large life cycle assessments and so on. But yeah, I think we really see a lot of potential different applications. And aside of this self-healing, we have the recyclability and the materials itself. They impose a lot of advantages in the manufacturing as well, and certainly for multi-material components. So we can really join things together, take them apart, put them back together, and do it for an infinite number of times. And then they can be fully recycled, or even if they cannot be recycled, they're biodegradable and so on. So I think, yeah, it will impact when we go with these robots outside of these confined environments where we have more control over them, towards the use of these soft robots in the environment we live in. We need to do it in a sustainable way, of course.
Brilliant. And just perhaps one question for you all just before we finish off. Mechanical embodied intelligence or AI, where do you see the future? How do we bridge these two together? I'm interested, Marco, what are your thoughts on mechanical intelligence? Does it fit into your framework? How could it aid you? And equally, on the other side, those of us working closer in mechanical intelligence, what do you think AI has to bring? How do we get the best out of these two kind of different approaches and bring them together? Or are they the same thing? I don't know if any of you would give us a final few words on that. Sorry, that's a big question.
Yeah.
Thrish.
I mean, if I may say something, so I don't see a boundary in intelligence, right? So it is a spectrum. It's a spectrum from very high plasticity, like in the brain, microsecond plasticity, to millions of years of evolution, hardware level plasticity, right? So all these things are needed because the statistics of the environment, we are mirroring the statistics of the environment. Some parts of the environment are changing at microsecond level, and then some things are not changing. It is like the terrain is terrain and things like that. So there are baseline things. So you can have hardware level adaptations to baseline things, and then you need synaptic plasticity to adapt to very high frequency things. All these things are really needed. So simulations, as I see, is like more like a model-based stuff that need parameter changes and adaptations, right? So that informs hardware level designs in the long run. So it's this full spectrum is needed.
Yeah. Any other thoughts before we finish this session? No? Brilliant. Well, thank you very much all for your talks. And I would really like to ask the panel, if you have some time, we have a talk after a short break now from Alison Okamura, and then we'll have a final panel discussion to reflect on the entire day. So if you are available to stay for that panel session, we would really appreciate it. But firstly, thank you very much to all the speakers and to Joanna. So we'll now have a break for 15 minutes and then we start back with the final plenary of the talk of the day from Alison Okamura. So just thank you very much once again, and we'll see everyone back in 15 minutes. Thanks.
Thanks, Josie.
Thanks a lot.